2013 is not the only anniversary. It's not only one anniversary this year. It's also important in the history of black holes. And just a little bit of potted history here. As everyone knows, in 1915 and 1916, under remarkable circumstances, Schwarzschild found a spherical solution to the Einstein field equations. And I'm just about to turn on my... right, there we go. And 90... That better? What? Well, you're all very old, so I thought I'd better shout. And Oppenheimer, who was not unknown in California at that time, and Snyder clarified but didn't completely understand what was going on with black holes, but it was understood, and in a remarkable feat of mathematical physics, Roy Kerr in 1963 was able to find the famous solution that bears his name. A lot of work by many relativists, some of whom I've listed here and some who worked here, clarified and gave us the picture we have today. And I think it's fair to say that as far as classical physics and astrophysics are concerned, we only need these solutions of general relativity, this description of a black hole, to do our business. Now, this doesn't understate the importance of black holes, particularly in quantum mechanics, and excited the febrile imaginations of the theoretical physicists in a most productive way, and fire marshals are out at the moment and so on, but I don't think this has any impact on astrophysics as we'll be describing it today. So just to review some of the properties of black holes as described by Roy Kerr there, there's a characteristic length and time and an energy and so on associated with a mass, just scaled here, as everyone knows. There's also 1 second parameter that is not just a scale, it describes the geometry, and that's the we can call that the specific angular momentum, which is limited for an astrophysical black hole, and associated with that is an event horizon which has an area which, according to a theorem due to Hawking, cannot decrease, and associated with that for our purposes is what we can describe as an irreducible mass of the black hole, which is different from the gravitating mass that will be measured by an orbiting satellite, for example. And the difference between the irreducible mass and the total mass is a reducible amount, which can be up to 30% of the mass of the black hole, and that is essentially there for the taking. Just a couple of more quick points which I'll need. One is equivalent to this specific angular momentum. One can define a spin of the black hole, and for many purposes that is as a better parameter used, but it can just be replaced by the specific angular momentum. And the second point to make is that it's a crucial property of black holes that when they are spinning, there is a region close to the event horizon, called the ergosphere, where a physical observer must be rotating with respect to the distant stars and so on. And I'll come back to this point in a moment. So many people put together this picture, and it's one that we confidently have, and we can solve. This is the background against which we can solve problems. The general relativity is not the problem. It's not the physics of the 20th century. It's the physics of the 19th century that confounds us when we deal with this modeling. So just going on now to jets. As I say, relativity is almost 100. General relativity is almost 100 years old. So brace yourself for that. But also about the same time was the discovery of the first jet here in California by Heber Curtis, everyone knows, in M87. And then an important development was by Jennison and Das Gupta in 1953, they discovered soon after the redshift that Cygnus A was not just a single source, but it was double. And here's their map, made with a very creative interferometer. And of course, interferometry developed. Many radio astronomers were responsible for that. And then that reached its fruition, and pay tribute to Ken Kellerman, Marshall Cohen, Erwin Shapiro, and many others who made VLBI an art and produced extraordinary resolution. And using this, we're able to demonstrate the prediction by Martin Rees of superluminal expansion. And I'm not quite sure what happened to that, and we'll comment on that a little bit more. The bottom line from all of this is that jets are very, very common throughout astrophysics, not just in the context of active galactic nuclei, but they are formed under quite generic conditions, and in the particular case of many active galactic nuclei, those associated with double. Okay, okay, so I have to remember to do that. In the context of many active galactic nuclei, one has this sort of layered structure where one sees jets all the way down very close to the black hole to the very largest distances. And we'll see it. Here's an early example of NGC 6251, which Tony Reedhead and his colleagues were able to develop, were able to observe. And this is a slightly more modern version of that, but it made very clear this continuity of the jet structure over many decades of radius. So we just, there's M87, sorry, it seemed to slip, and this shows that there's, this is an imaging down to the scale of about 100 times the size of the event horizon of the black hole, and one can find VLBI fringes in recent observations down to the scale of about 10 times the size of the black hole. This is truly remarkable, and maybe even more is to come. So here's just a rogues gallery of jets. Of course, there are thousands of these things now. Cygnus A, you can see there. Picture A is really this is an X-ray jet, not a radio jet. You see the black hole on the left-hand side and the beam dump, as it were, on the right-hand side. Extraordinarily straight. Again, a remarkable natural phenomenon that cries out for explanation. So let's now turn actually to the topic of this meeting, and let me say how delighted I am to be here to honor both Maarten Schmidt and the discovery associated with him and his many colleagues. Maarten has been a colleague for myself and a role model for nearly 40 years, and I'm really pleased, Maarten, to be here sharing this time with you. I thought it might be nice to sort of illustrate what's going on by sort of specializing to the particular case of 3C273. And here's just some sort of features of the many observations made over the years of 3C273. It is, of course, an extremely luminous quasar, very close by to us, about 10 to the 46 ergs per second. It's associated with a galaxy, which is now, in fact, a giant elliptical galaxy that's comparable with the brightest cluster galaxy. The black hole mass has been estimated using reverberation mapping, as Brad told us about yesterday. It's stayed under a billion solar masses, and that gives it a size of about just over 10 to 14 centimeters. Early work done here using hybrid mapping and so on was able to show not just things moving at 10C, but actually moving along a jet, expanding by Reedhead and others. So it was about 10C, and that indeed remains a good speed estimate. You can see, for the younger people here, I should say, this was done in the days before computing. You can tell because of the squared paper that was used there for making the maps. But okay, never mind. At any rate, now here's the full spectrum of pictures, and you'll see a lot more from Meguri coming up, but this is just in the case of 273, and of course at low energies one believes was looking at the synchrotron process, at high energies was looking at the inverse Compton process, and in between one is seeing the thermal emission from the accretion disk and all that it illuminates, and this is sort of probably almost certainly an overrepresentation in terms of the non-thermal parts of the total bolometric luminosity, because it is beamed towards us And so you should suppress the left-hand side and the right-hand side, but the amount would be somewhat controversial, but it could be quite a lot. In terms of observations, I'd like to sort of linger a little bit on the gamma rays. And this epitomizes what's going on in a lot of other gamma ray observations. It is highly variable, of course, all throughout the electromagnetic spectrum, but particularly in the gamma rays. And in this particular source, the most rapid variation is on a time scale of hours. And so, I just show one time series from observations of this made with Fermi, and the highest energy photon is 15 GeV. Now, I'm going to linger on this a little bit because it brings out an important point, which is that in order to get a 15 GeV photon from this highly luminous environment, it has to be created sufficiently far out that it doesn't encounter a photon with an energy of about the Lyman continuum on which it will pair produce. So that's a lower bound on the radius of emission or creation, or I like to call it a gamma sphere, like a photosphere, and that works out to be about 30 parsecs for that particular photon. Now, this isn't what is always represented, but the very existence of that photon is remarkable, and same things happen in gamma ray bursts and so on. People say the lower energy gamma rays can come from closer in. That's right, but it does say we've got to do a lot of particle acceleration quite remote from close to the black hole. How remote and so on, and you can see it's going on all the way along the jet. It's 25 kiloparsecs in projected radius and 10 times that in real physical radius, way outside the galaxy. So there's just a few things about 3C273. So 3C279 shows much the same. I'm not going to linger on these at all. Just say that as with 273, you know it's synchrotron radiation. Believe it's synchrotron radiation because you see highly polarized emission. In 279, it's even more polarized, about up to 30% or so. You see correlated variations, particularly in the polarization, organized swings of the plane of polarization and so on, suggestive of a strong magnetic field. And there are dramatic examples of that. Even more dramatic examples of gamma ray variation come from TeV, not GeV astronomy, but TeV astronomy. And here one sees variations, particularly in the BL-Lac objects, on timescales as short as minutes. And that's extraordinary. And they, in an even more pregnant way, illustrate this problem of having to get rapid variation from a region that has to be sufficiently far out that the photons can actually escape from that environment. So I'll returning to this point. The observational situation, and I should also say one other very important point, and in fact the work at Owens Valley has been doing this, is we're now starting to see the results of the multi-wavelength campaigns that are looking for cross-correlations between the variations at different spectral bands, and in particular, it looks like the gamma ray observations in the best studied sources precede the radio observations, which suggests that the gamma rays happen from inside the region where the radio is produced. So we're starting to piece together a sort of anatomy of these jets. But then the challenges to trying to explain it are even stronger than they've been for a long while. So Markarian 421, which recently went berserk, raised its flux by the gamma rays and X-rays found by New Star by about a factor of 20. These are not small changes, not subtle changes, some parts of the spectrum. And yet there's contrary indications from the observations. This is work from Alan Marshall and colleagues, which shows in 3C120, where it's argued that some of the gamma ray variation comes from enormously far out in the jet. In this case, maybe 100 parsecs away, because there's correlated variations. Well, obviously, we're a little bit undersampled here still, but this is something that should be and can be, I think, sorted out in the very near future to sort of unscramble this and find out what's going on. And then I can't resist just showing, sorry, going the wrong way, the Crab Nebula. It's one of many examples of what I think is increasingly common phenomenon in high-energy astrophysics, where here, as I'm sure many of you know, again on the time scale of hours, again from a region that's parsecs in size, that's light years in size on the time scale of hours, one gets variation in the gamma ray range. This is a challenge, and it requires regions that are overpressured with respect to their environment. So let me just sort of summarize this highly selective view of the observations, just specialized right down to the business of jets. They're very common. We see in young stellar objects, gamma ray bursts, and so on. And so it's a very generic thing to happen. I think the circumstantial evidence is that magnetic fields are strongly implicated, and I didn't mention, but in 2C273 I should have said this, the rotation measure is enormously high. That again is an indication that there are strong magnetic fields that are involved here. The gamma ray variation typically varies on sizes much smaller than the jets, on timescales much smaller than the light crossing times of the sort of regions where they have to be located, suggesting either ultra-relativistic beaming or an idea that I shall pursue a little bit more, that you have overpressured regions inside these jets. Okay, so let me now segue onto theory, and I'll just review this very fast, because I think many different ways of doing this. There's a sort of general idea is one of unipolar induction, and basically if you have a spinning object, in this instance a black hole and perhaps the inner parts of an accretion disk, then there'll be a certain magnetic flux associated with a certain EMF that's induced. You're working electromagnetically, so there's a current and a power that go with it. And if you want to match an AGN as opposed to these other ones, then you're something like 3C273, you're talking about almost a zetavolt, which is adequate but not required for the ultra-high energy, most energetic ultra-high energy cosmic rays, and also allows protons to be accelerated if you happen to think that the emission in these jets, which I don't, comes from protons, but several people do. So these are sort of prodigiously energetic things, and this is all done if you have a spinning massive black hole and about 1 Tesla worth 10 to the 4th Gauss of magnetic field threading it. So this is all sort of very old news, but just getting everyone on the same page. Looking a little bit more detail at what might be going on, and this is, talk about here, this is obviously things that I've been interested in, but particularly I've learned a lot from my colleagues here at Caltech, Peter and Kip and Sturl especially, and the basic idea, this is sort of a picture of something I did with Roman Zyko some time ago, is that you have magnetic field lines that thread the horizon of a black hole. They also thread the accretion disk, and they can take that reducible mass, they can take that energy, and that can be powering the jets. Just to be a little bit more specific about this, if one tries to think about this in the most simple way, and that's something I'm going to push a little bit, and you don't have to do this at all, it's the existence of essentially symmetries in the problem allows one to define conserved quantities, specifically energy and angular momentum, in the simplest sort of expression of this, and that then enables one to define currents and potentials and angular velocities and so on associated with the field lines, and applying boundary conditions then essentially allows one to solve in a relativistic formalism what you can make an analog of in a flat space, which is driving essentially a large circuit and having currents flow as a result of the induced EMF. And you can make a sort of something I would recognize from electrical engineering or whatever. The angular frequency of the field line is a sort of compromise between the angular frequency of the hole, and then just depending on what the effective resistances are, and the angular frequency of the load, which might be 0, or it might be something associated with the accretion disk. And these resistances are all round about the impedance of free space 100 ohms. So this is the way it sort of works out. And in terms of power, the work done by the torques is balanced by the energy dissipated inside the hole and the energy dissipated inside the load. And this is what the observers are interested in, of course, is what's dissipated in the load, because that's the emission from the jets. Just throw out these two possibilities. This might be one cartoon of what field lines look like on the left-hand side, going straight to the disk, sort of dipolar configuration. This might be one that's so a quadrupolar configuration. It's a different type of field geometry. It has some advantages. So just hold that thought for the moment. There are these two possible choices. And for a long while, we were sort of, just dealing with cartoons like this and sort of axisymmetric calculations we could do. But thanks to 20 years of hard work by many people, including Dave Meyer, who's here, it's been now possible to do numerical simulations that are extraordinary, both in the context of force-free electromagnetism, but also of magnetohydrodynamics. And the ones I've had to show you are like this, so let me just get those going. Let's just get going. And you can see these particular ones are ones that are done by my colleague Jonathan McKinney and Sasha Tchaikovsky, and there are many others around. And this is not like doing these simulations in the early universe, where one thinks one is simulating and putting in all the physics and doing things that one can compare with observations and so on. This is really much more like a computational laboratory. It's actually doing experiments that teach one things, and after the fact you say, I wish I'd thought of that ahead of time. So, and then a bit later you say, I did. So this is a we started off in generic initial conditions, and you can see the jet forming here, and then we did something perverse to it and changed the direction, the polarity of the field, just put it in by hand. What's peculiar about these is that we put in very strong fields from the start. So we assume that there were strong fields there, and then show that the jets are then self-sustaining. And the one thing, I won't go through all the way through this, but the one thing I want you to notice is this sort of hula hoop type motion of the jet. There's a regular sort of quasi-periodic pulsation. This is an example of one of the many discoveries that we made from the simulations. And after the fact, it does make sense. So let me just sort of summarize a little bit of, obviously what's come out of these and other simulations, is that jets are, despite being three-dimensional, are robust and collimated. And you can trace these things out now to about 1 million M. So you can actually do some interesting experiments with them. You build up strong fields they're highly sustaining. In fact, they're so strong that they suppress the famous magnetorotational instability. They don't allow that to develop. They demonstrate that it is in fact possible to extract energy efficiently from the jets. In fact, you can take more energy out from the jets than you're putting in the accretion. So the efficiency can be more than 100%. For the collimation, one has to also put in the physics of the winds and so on, and that sort of needs more work. This quasi-periodic oscillation is something that actually people are looking for now observationally. Again, one also sees sort of intermittency and so on, which is what one would like to see in terms of the observations. And so there's a lot more. And then I think one thing I emphasize this quadrupolar versus dipolar geometry. What we discovered, and after the fact it made sense, is that the quadrupolar geometry does not make jets. You need the dipolar geometry. This is an example of the sort of thing that you can learn from simulations without having to rely on the detailed quantitative output. Here's another one. Again, I'm not going to go. There we are. This is a jet somewhat similar with a thick disk and strong magnetic fields. But what we did here was just artificially tip the black hole and tip it by a large angle, and then what you'll see is that the jet actually emerges along the spin axis of the black hole, but then orients itself perpendicular to the disk that's at larger distances. And this is an effect that's been attributed in the past to the so-called Bardeen-Peterson effect, a purely gravitational effect. And in fact, what is going on here is that's completely irrelevant. It's all done by magnetic fields. So this a relationship of the jet axis to the disk axis is mediated by magnetic field, not by gravity. So again, this is an example of something that you can learn from this. So I'd like to sort of finish up by going into particle acceleration, and in particular, what might be going on inside the jets. And I sort of emphasize what some of the problems were. We need to be able to make this very rapid variation at some remote distance. Even the minimal lower bound on the distance still is a major challenge. And there have been various ideas out there. It's almost certainly, and it's certainly optimally happening in an electromagnetic environment where the electric fields are comparable with the magnetic fields and so on, and greater than the particle fields. And I'm going to assume that because that in some sense is optimal. Now the ideas that have been, each of them could take a whole colloquium, reconnection, but done in a relativistic, done relativistically, shocks, turbulence, jet turbulence, anyone who lives near an airport know that happens. And then more interestingly, because we've got large-scale organized fields, is pinches. And those are well known to be unstable, and that leads to a new sort of structure that I'll call a magnetoid. It's not a good word to use in this context because Ozanoi previously used it, but I'll call it that and call it something else. So basically, the point that I want to make here is that a possible emitting structure is something that is not just a magnetic field like in a pinch, but one where there's a linkage in the magnetic field, where flux lines sort of intersect each other like that. And we know of precedents for this in the laboratory. It has a quality called helicity, which I won't completely define here, but I did there. And here's an example. And it's not a mathematician's fiction because Paul Bellin, who works here, makes these things. And furthermore, as I expect Maarten knows, Lo Vulture, in his 1958 work on the Crab Nebula, did a lot of the initial thinking about the importance of helicity in a relativistic magnetic environment. And so this is an example of the simplest type of magnetic structure. I call it a magnetoid. If you generalize it, that's called a spheromac. And basically, it's confined by external field, but it contains regions inside it that are very overpressure with respect to their environment. And it's a rather precarious equilibrium that you can create. You can classify these things, you can generalize them, and so on. I'm not going to go through all the mathematical details of this, but you can essentially organize the solutions to these. They're sort of generic, not special cases. And the basic idea is, because of their precariousness, you can, here's the problem solved in Cartesian geometry, and then in spherical, sort of quasi-spherical geometry, you do that. And then basically you have these regions that are organized by magnetic surfaces, and if you stress them and strain them, they will go pop. They will buckle essentially. The magnetic fields will buckle and move to a lower energy state discontinuously, thereby liberating all the magnetic energy. So if you do that, so that might be what's going on inside a little jet. Very satisfying. So just to finish very quickly, what the horizon is. Clearly, we've got to learn more about magnetic fields. This is heroic stuff in VLBI to do this polarimetry in this way. But what we would like to see is, do we have magnetic fields wrapped around? Do we have these helical structures very close to the black holes? A lot of good work being done there. I think more possibilities coming along the line. Imaging a black hole, obviously, with the Event Horizon Telescope, and that's what ALMA looks like. That's what it's going to see, maybe. And very nice simulations and so on. And then just summarize, spinning black holes are common. The jets are probes of what's going on in the holes, and we've got a lot of new obvious approaches to particle acceleration and new results coming on the line. And thank you, Maarten, and everyone else involved for giving us so much fun over the last 50 years. Thank you. Oh, you only saw the innermost part of the simulation. The simulations actually go out to now about 1 million M.
No, but you showed they weren't very collimated, so they were still pretty...
Well, that's very close to... they're more collimated than the best observations we have, which is in M87.
Okay.
So
That's not an
No, it's not an issue. No, no, they become more collimated. But I think, to describe them at greater distance, you'd undoubtedly want to put in more physics than went into these simulations. I should say this is, there's a lot more physics that has to be put in. There's comparable set of simulations for accretion disks and flows and winds from accretion disks. And those have got sort of, in my view, comparably sophisticated. And melding those two is something that needs to happen. Yeah. Mm-hmm.
Is most of your momentum electromagnetic in the jet, or is most of it the other way?
Momentum is, so when it becomes relativistic, it's more the same as power. And basically what I would envisage, and this is not part necessarily of the simulation, is that the jets start off as basically electromagnetic, they become relativistic hydromagnetic, they entrain material through the walls, and in particular the interstellar clouds that they pass by and so on, and they entrain those too. And by the time you get out to the working surfaces of the double radio sources, they're probably heavily loaded with ionic plasma. But my current prejudice is, and I can't demonstrate this case, although there is some observation support for this, is that they start off as highly electromagnetic electron-positron jets. But it's a transition as you move outwards, and where those transitions occur depend on what the environment is, what the powers are, and all the rest of it.
Gentleman in the back.
You mentioned Kerr, and this being in Kerr Shield, and this being the 50th anniversary of that. Anyone can come to me and ask for more details if they want, but it's not very widely known that Roy Kerr was about to be terminated for lack of productivity when he discovered the Kerr solution. He walked into Alfred Shield's office, and Shield was aware that the administrator of the grant that he was there on as a visitor had actually written a letter, and it was in the mail to Kerr telling him he was going to be terminated. And Shield had to scramble in order to intercept that letter so that Kerr never received it.
So the termination refers to his academic employment, I trust.
I use termination rather than the other American euphemism, which is let go.
Oh, okay.
Okay. Tony, last question.
Roger, the quasi-periodic oscillations that you're referring to are
Yeah.
short timescales, but as you know, we've seen one that's very rare example of quasi-periodic oscillations in the objects that we're monitoring. Their timescales are sort of months to...
Yeah, no, that's a completely disjoint timescale. Yeah.
What do you think is causing the other quasi-periodic oscillations?
Oh gosh. Well, I mean, you can find. I mean, you have sort of seen things like this in Kelvin Helmholtz simulations of jets, where people have done jets, and you can sort of create sort of wiggling structures that are spatial modes and so on. And I think it, if it's a widespread phenomenon, I think you could probably excite them at some particular radius in the surrounding medium where there's perhaps a change in the pressure or something like that. Mm-hmm. So I think it is possible to do it.
It's not widespread, it's very rare.
Very rare, but that would have to happen on a be initiated on a much larger scale in the event horizon, which what we were describing was something that happens essentially on timescales of hours typically.
Shall we thank the speaker?